Hello, it's Mr. Dobson again, and welcome to my fifth video on gravitational fields, this time about potential gradients. So at the end of the last video, which was on gravitational potential, we got to the point where we were considering equipotentials, so lines where the value of V, gravitational potential, V being the work done per unit mass to move from infinity to that point, where the value of V was the same. So if you was to move in this direction, you would not change your value of V. And we actually realised that has probably something to do with why things tend to move round objects like this, but we'll come to that later when we do satellite motion. But if we was to move in this direction, we would change our value of V. So potential gradients, what are we talking about when we're talking about potential gradients? So potential gradients are a measure of how, in essence, how closely spaced these equipotentials are. So the potential gradient here is very high and the potential gradient here is very low. Now, sometimes I think it's best to consider this if we was to be able to take this image here, cut it in half and look at it sideways on. If we was to do that, we would see that we'd have a graph that would look something like this. This being radius as we move away from Earth, or change in radius. This being V. We'd have a minus 63 number down here, mega, and that's in joules per kilogram. And we would move in this direction as we moved away from Earth. So what we would see is that the value of V gets closer and closer to zero as we move away from Earth. Now, as I explained before, when you look at the idea of gravity wells, if you was to take points on here of equal potential difference, so say these are points of 10, change of 10 V each time, and you was to mark them across onto this side, what we would see is that the lines we would get, the points where we would intersect here, would start off close together, but as you moved away, get further and further out. That looks exactly like the shape that we have here. So as you can see, this is how it looks if we look from the top. Here is how it looks if we look from the side. So that gives you an idea why we've got this shape. I'm just going to get rid of all these lines now because they're a little bit, making it a bit more complicated than we need it. That's just to explain, I might have to get rid of the whole thing and start again because my pen is not accurate enough to just do that bit. That just now explains how we can draw it that way. So I'm going to draw back exactly the same graph. Okay, so at any point on this graph, because it's a curve, we can calculate a gradient at that point. Now, if gravity didn't change, if things were constant, we'd have a straight line. We'd have a line up here. We could have a constant change. But that's not what we have. We have actually a curve of some description, and therefore to calculate what's happening on that curve, we're going to need to use a tangent to that line. So we can see that a tangent to the line down here will be something along that angle, and the tangent to the line up here will be something along that angle. We can see that the gradient of the line, as in how far it is like this, the steepness of the line, changes as we move out. So what we're seeing here is that we have a steep gradient close to the Earth, a very steep change in V as we move away, and as we move further out, a very shallow gradient, a very small change in V as we move away. So going back to our original picture, that explains what we mean to some degree, that the potential gradient is a kind of a measure of the distance between these lines, but it's a measure really of how quickly V is changing as we're moving away from Earth. Here, V is changing very rapidly as we're moving away from Earth, but as we get further out, V is changing less and less. So this is what a potential gradient is. It's how it's changing. We can actually define it mathematically as well, because the potential gradient is going to be a change in V, because we're looking at how quickly V is changing, over a change in R, because that's how you would calculate a gradient on the graph that we just did. To work this out, you would look at the change in height over the change in run, or the rise over run. So actually, if I wanted to calculate the gradient of this line here, for instance, I would have to look at this change in V over this change in R, and I would then have the gradient. So we can actually calculate gradient mathematically as this delta V over delta R, and that's what a potential gradient is. It's quite important because actually, as you can see here, we see this delta V over delta R in this equation. Somehow it relates to G. So why does it relate back to G? Obviously that might be a very useful equation in exams, so we might want to know how that works. Now, to see how that works, we need to set up a scenario. So let's take the scenario that we have a surface of, say, Earth, just for argument's sake, here, and because it's Earth, it has field lines which will look uniform because we're very close to the surface of Earth rather than radial. They face in this way. Theoretically, it has some lines of equipotential. I know they're not drawn properly spaced out, but that's fine. So this is sort of lines of equipotential here. And I'm going to move an object. I'm going to take an object that's here, and I'm going to lift it to here. So I'm going to have to move that object. I'm going to try and move that object through a distance delta R. I'm going to change the radius of that object slightly. Now, when I do change the radius of that object slightly, I'm going to have to do work, because there's a gravitational field. The gravitational field of the Earth is pulling down on the object in this direction with a force W, the weight. So there is a W force, a weight going down in that direction, and if I want to move the object up, I've got to fight against that. I've got to do work, and that means I've got to apply a force in this direction, and these will be equal and opposite. So we can actually write that mathematically, that the force I will need to apply will be equal to minus the weight. Or way we tend to write that instead, actually I won't write equals, we tend to write that instead is that mg, being the weight, is equal to minus F. It works better around that way, you'll see later on. So the weight is equal to and opposite to the force that we would have to apply to move it up in the field. If we were to move it in that field, we would change its gravitational potential. It would have a value here at the bottom of the field of V. You have a new value up the top here that is not the same, that is a change in V. So it would have a value here, V plus delta V. Now, you might think, hold on, why have we said plus delta V? Surely it's going to get to us nearer to zero. We know these are negative numbers. That's true. When I say V plus delta V, all I mean is that there will be a value of V here, and this will be equivalent to that value with a change in it happening. If it turns out that the change is the opposite way to I think of it, then this will just be a negative answer. It will cancel. It's not actually a problem. I'm not worried about whether the change is up or down, just that this is a change from this state. So we're going to move it from here to here. We're going to apply a force. There's going to be a change in V as we move up here, and we can do a little bit of maths to that. First of all, we can take the equation that we have over here. I think my pointer there. This is obviously our equation for the work done to move an object in a gravitational field, which is interesting to us because we just said that we're going to need to do work, and we've done a calculation of that, so it's clearly going to become important. So we can take that equation as the change in V is equal to the change in W over M. Now the change in W, that's the work I'm going to have to do. And we said the work I have to do is going to be, that's the work done, not the weight, by the way. This up here is the weight. That's why I changed it to mg instead. This is the work done. So this is a change in, doing work is going to require me to move a force for a distance, because we know that work done is equal to force times distance. And therefore, in this case, of course, we can actually change that slightly, because the distance I'm moving we've got a value for. We've called it delta R, so that would be force times distance, like that. Combine these things together and we can actually find that we have, if I move up a little bit, delta V is equal to, now I'm going to substitute force times distance in for work, so F delta R over M. I'm going to rearrange for F because I'm actually interested in the force I would need here. So if I rearrange for F, I'm going to move the M to this side. I'm going to move the delta R down to the bottom. So I'm going to get that F is equal to M delta V over delta R. I've then now got F here. I had F up here, so I can use that. I can recombine with, actually it's that F I want, that one there, and I can say that mg would be equal to minus m delta V over delta R. So that's just a combination of this equation and this equation. The keen-eyed of you now would have spotted a simple cancellation that we have there, and we now find ourselves with this new equation, which is that G is equal to minus delta V over delta R. So what that tells us is that gravitational potential is the negative, or the opposite, opposite is not the best word, is the negative of potential gradient. So we have this situation. The negative, all that really means is it's sort of, it's to do with the fact that this gradient is going this way and gravity is acting this way. It doesn't actually mean that as one's going up, the other's going down. That would mean it's on the bottom instead of on the top. So the negative is just a directional thing. We can actually ignore that to some degree. The important point is that G is actually a measure of potential gradient. So we've come full circle. We started off with G in our first video, and we've gone through loads of other options. We've come back to this idea of these equipotential lines here, and if they're very tightly close together, we have a large gradient, potential gradient, and therefore we have a very big G. And as we move away, these lines get spaced further out, we have a smaller potential gradient, and we have a smaller value of G. So we've come completely full circle, the idea that G is very big towards the surface of the Earth, but as you move away, it gets smaller and smaller and smaller. So that is an explanation of potential gradients. It's also the last equation from the formula booklet that we've done. We've done all these equations now. They're all in there. You also see we've got G and the constants and some astronomical data that we're going to need. The only other thing left to do, there'll be 2 more videos on subject matter, and one of them is on the graphs that we will draw for these different situations, and on satellite motion, and then that is the end of gravitational fields. So we're nearly there, but we've gone from G through Newton, through a general version of G, through gravitational potential, and then finally back to G again, which is quite nice, full circle. Okay, thank you very much.